Okay, so where we left off in the last lecture about electric potential is we defined that the electric potential at any point in space due to a point charge is VKQ over R. Okay, so if a point charge is located a distance R away from somewhere in space, point A, if you will, then the potential at location A is simply K, the value of Q, divided by the distance between the point and the charge. And what we saw is that if we have 3 or more charges, well, it's really easy. We can find the potential due to all those charges by simply adding the potential's contributions from each charge. And so in this Got the Concept, we are going to be summarizing everything we have learned up until this point. Okay, so read carefully. We have 4 point charges, and they're each moved through a potential difference. Okay? Rank the charges, the electric potential energy of the charges, from most positive to most negative. So we're ranking the electric potential energy. So the information that we're given to find the electric potential energy change, delta U, is the charge value, Q, and the potential increase or decrease, which is a delta V value. So we need to put together everything we've learned so far. And if you look at those 3 variables, you probably off the bat can remember this relationship that we saw earlier, where delta V is simply equal to delta U over Q, right? So in other words, since we're solving for electric potential energy change, delta U, we're going to solve for that, get Q delta V. So all we need to do is use this relationship here to find the change in energy that each charge experiences as it moves through a potential energy or a potential change. So for part A, our delta U value is simply going to be equal to Q delta V. Our Q is positive, and our delta V is an increase, right? So that means it's a delta V greater than 0. So it's positive value, positive 5 volts. And we multiply those together, we get a positive value. And the units are joules for energy. Okay, what about part B? We put in our charge value. And then it's moving through a decrease. Okay, so that means our delta V is negative, right? Because it's getting smaller. So the final value is going to be less than the initial value. And a small number minus a big number is a negative number. So that's going to be minus 2 volts. Okay, and that gives me a negative 0.0040 joules. And so I think you get the pattern. So I'll let you guys do the rest on your own. And you'll be ranking them from positive to negative. Okay, so remember in this equation right here, there's no negative signs. Okay, so the relationship between delta U and delta V is a positive one. The only thing that could change the sign would be if Q is negative or if delta V was negative. So we wrap up this section, and it's a really good time to review because we've, thrown a bunch of equations at you and they all kind of sound the same, right? And they all kind of look the same. So let's review. The electric potential at a certain position equals the electric potential energy per unit charge for a test charge at that position. So what is that sentence saying? It's saying that V at a certain position equals the energy at that place per unit charge, right? And we just saw in the previous example that the change in potential equals the change in potential energy over unit charge. And we saw that when we look at an electric potential, it decreases as you move in the direction of the electric field. Now, why is that? So remember that negative charges have electric fields that point toward them, right? Electric fields are, they like negative charges. They're toxic. That's how I remember. I make some silly, association in my brain and I don't forget it, right? Electric fields like toxic people. They like negative charges, so they're always pointing to it. And so, right, these are little electric field lines. And potentials are little rings around the charges. And the value of each potential is V equals KQ over R. So if Q is negative, then V is negative, right? And the closer you are, the bigger the potential, right? Because the smaller the R, the bigger the V. So it makes sense that you as you move down an electric field, closer to a charge, a negative charge, you are going into lower and lower potential, or the electric potential decreases. So let's look at bullet point 2. The electric potential due to a point charge is positive if the charge is positive. It's negative if the charge is negative. That's really what I just kind of showed you right here. And why is that? Well, that's because the potential is simply equal to KQ over R, right? So if Q is negative, V is negative. If R is small, V is big. If R is big, V is small. And that explains this second sentence, right? The electric potential due to a collection of charges is the sum of the potentials due to each individual one. We just talked about that 2 slides ago, right? So the total potential at one point is going to be KQ1 over that distance, KQ2 over the distance from Q2 to that point that we want to know the potential, and so on and so forth. The electric potential difference between 2 points equals the difference in electric potential energy per unit charge between those points. So the electric potential difference between 2 points, so for example, that would be a delta V, which equals V at position, the final position minus V at the initial position. So if V at the final position is equal to KQ over R final, KQ over R initial, okay, that's equal to the energy change per unit charge. So, right, that's our original definition of potential. It's just telling you that this is also true if you decide to express potential due to an individual point charge. So we're going to move on to the next section, and it's completely tied to what we're talking about. It's just a visual of electric potential. Okay, so we're going to talk about visually what electric potential is, those rings around the charges that I mentioned already. And what are those rings called? Those are called equipotential surfaces. Okay, so this is what we're going to be talking about, the visual of electric potential. So to kind of introduce you to electric equipotential surfaces, let's think back to an example that we had way earlier in this electric potential lecture series. So the very beginning of the previous lecture video, where we found the change in potential of a charge moving in an electric field. And we saw that we can express the change in potential in terms of electric field like this. And we found the electric potential difference of the charge moving from point A to point B. And then we found the electric potential difference of the charge moving from A to C. And we saw that those values were the same, right? They were both 60 volts, right? Delta V between A and B and delta V between A and C were both 60. And so we didn't really talk about why that was or what that means, but what that means is that if that particle were now instead to travel from B to C, right, the potential at B is 60, the potential at C is 60, what is the change in potential going from B to C? Well, that's 0, okay? And so what does that mean? Well, that means that the particle does no work to move along that path. And the other thing that means is that means a couple things, right? You're moving 90 degrees to the E field. So that mathematically shows you that delta V is 0, right? Because you can see plainly that the E field is in the x-axis and you're moving in a displacement that is perpendicular to that. So mathematically delta V equals 0. But what really is happening is that charge is moving along an equipotential line or an equipotential surface, depending on if we're talking about a 2D or a 3D picture. Okay, so physically that means that the particle does no work to move from B to C. So anytime that you move perpendicular to the electric field, okay, you're moving along a line of equipotential. So these equipotential lines, the potential is the same value. And so that's why earlier you saw me draw, it doesn't matter if it's positive or negative charge, right? We saw electric field lines from positive charges are directly away, radially. And then the equipotential lines are circles around it because guess what? These lines are perpendicular to circles, right? The electric field lines are perpendicular to these circles. And the potential value at those circles is KQ over R because the potential is constant for a constant value of R, right? So if this is a radius of 5 centimeters away, well, the potential due to that point charge Q is going to be the same anywhere along this equipotential line, okay? So if a particle were to move along the equipotential lines, okay, it's going to have a change in potential of 0 because the potential is, if it's 60 here, and then it's 60 here. Okay, so equipotential lines are perpendicular to electric field lines. And it's simply there to tell you what is the value of the potential at that location due to that point charge. So, depending on, if we're talking about 2D or 3D, right, we can be speaking about a surface or a line, but they're both locations of equal potential, right, equal potential. And like I said before, no work is required to move a charge along an equipotential surface or an equipotential line. And we can see that mathematically, right, if delta V is ED cosine theta, well, if E and D are 90 degrees from each other, then delta V is 0. And that means that delta U is also 0, right? Because delta U is QED cosine theta, a negative sign. And if delta U is 0, well, we know that negative delta U is equal to the work, so the work is also 0. Okay? So here's another kind of schematic of some electric field lines. So these are not necessarily uniform, right? They're curved. So, but that doesn't matter because if you draw a line that's perpendicular to every point on that curve, that blue curve, then you're going to have yourself an equipotential. So everywhere along that yellow line has a constant potential, in this case 0. Everywhere on this equipotential line is going to have a value of 50. And so what we can do is we can imagine, to help us kind of see this trend of why it's getting larger going this way and smaller going this way for potential. Well, imagine what's creating that electric field line. What are creating those electric field lines? Well, they're pointing directly away, so there must be a positive charge over here somewhere creating those electric field lines. And we know that electric field lines point away from positive charges, and we also know that the electric potential is positive for positive point charges. They get bigger as R gets smaller, right? So the closer we get to that positive point charge, the stronger V will be. And that V is going to be positive. So you can read through these slides. It's kind of like I kind of speak faster than going through and reading each slide, but there's a lot of good information here. It's pretty much summarizes what I've said. So now let's look at these pictures I've been drawing with the circles that are perpendicular to the electric field lines, right? So here are our charges, our point charges, and the blue lines are the electric field lines. And you can see that the equipotential surfaces are circles around those charges. And so let me ask you real quick, how would we compare the value, let's say, of this line to this line, right? Well, this one is going to be more positive. This one is going to be less positive, right? Because the potential is going to increase as you get closer to the charge creating the potential. And then if you look over here, well, this one is going to be super negative. And then out here, it's going to be less negative. And so now we can relate potentials to electric fields, right? What we saw earlier was that electric field lines go toward regions of lower potential. And we can see that right here, right? Electric field line is moving from a more positive potential to a less positive potential. And here the electric field line is moving from a less negative potential to a more negative potential, right? To decreasing potential. So in both cases, E fields move toward decreasing potential, always. Doesn't matter if the positive charge is creating that or the negative charge is creating that. In both cases, they move towards decreasing potentials. The electric field lines do. So, equipotential volume, right? So, don't worry about this. Don't worry about equipotential volume. There's some things we can't cover all of the chapter. Okay, so don't worry about equipotential volume. Let's do this. Got the concept, okay? Which centers around this image here. All right. So this is going to tie our understanding, our relationship between E and potential. So in this graph, the orange vertical lines represent values of the potential along an x-axis. All right. So here at 2 meters, we have -1 volts, and at 3 meters, we have -2 volts. So it looks like the potential is decreasing to the right. Okay. The question is, which statement is correct about the E field at point A compared to point B? So from A to B, let's see what qualities we're comparing here. So if we look at part A, at location A, the field points to the right and has a greater magnitude than B. So we're basically trying to figure out what is the direction of E. Okay. So while we just talked about that E points towards regions of lower potential, right? So if V is decreasing to the right, well then E should also point to the right, right? So E points along, V decreasing. So our E should definitely be to the right. So it looks like we have a choice between A and B. Okay, C and D we're going to rule out because it says E points to the left. And we know already that E always points towards decreasing potential. So now let's take a look at the magnitude of E. Okay, so the magnitude of E, how can we understand that better? Well, the magnitude of E is going to be stronger the closer you are to the point charge that is creating the E field lines, right? So if E is pointing this way and the charges are getting more, the potentials are getting more and more negative as you move to the right, well, then the E field over here should be stronger than the E field over here, right? Because if I look at this and I see the potentials are all negative, well, that's going to tell me, number one, that a negative charge is creating those potentials. So there's a negative charge over here creating those potentials and spitting out field lines, you know, right here like this. So since I am going to be closer to the negative charge at the direction that the E field is pointing, I should have a stronger E field the closer I am to the charge, right? So the magnitude of B should be greater than the magnitude of A. So let's see which one correctly states that. So at A, the field points to the right and has a greater magnitude than B. No, so A does not have a greater magnitude than B. B has a greater one than A. So, or in other words, A has a smaller magnitude than B, right? So B is the correct answer. And so to answer this question, the two concepts we used is the fact that E points along decreasing potentials, and also that the lower potentials, or the most negative potentials, are going to be closer to the point charge, right? Which means that the E field closer to the point charge is going to be stronger, because both potential and electric field are inversely related to the distance, right? So the bigger they are, the smaller they are. So there we go. And so just as a reminder, the explanation for each of these got the concepts is in your book, okay? So if you found my explanation maybe a little confusing, or, you're going through all these videos and you just need a break from hearing my voice, you can go in the book and read their explanation. Okay, so that's it for this section, right? I was just kind of finishing up our discussion on electric potential, which was quite long, but we have, it's a little bit of a conceptually difficult topic, but I think once you see the pictures and you connect it to electric field, it's going to make a lot more sense. So these pictures here, if I just scroll back quickly, right, these two right here are going to be your best friend in understanding the word problems that are relating potential to electric field. Like, as far as decreasing potential is the direction that electric fields point, and questions like that. So I'm going to just wrap up this video here, and then we will pick up another video starting a new topic, capacitors.